Hi, this is Ross Spencer. I'm going to try to teach you physics this way. I was reminded as I thought of what this is going to be like of Boccaccio in 1350 wrote a story called The Decameron about a bunch of people in Florence, young people, 7 women and 3 men who went out to a villa in the countryside to escape the Black Death, which killed 20% of the people in Florence around that time. And to pass the time, they told stories. So that's what I'm going to do. I'm going to tell you physics stories about relativity, and quantum mechanics, atomic physics, nuclear physics, and then finally, particle physics and the way the universe is built, as nearly as we understand it as physicists. So here we go. Einstein's theory of special relativity. You've probably heard about this your whole life. We're finally going to do it a little bit. Okay, so here's where we've been in physics so far. In 121, you studied stuff from the 1700s and the 1800s. In physics 220, when you take that, you're going to mostly spend your time in the 1800s. And in 123 so far, we've been in the 1800s. Only got up to sort of the late 1800s in what we've done. We're finally going to move into the 20th century with relativity. This all happened in 1905, and it came from the fertile brain of Albert Einstein. Here's a quiz question from your reading. Special relativity is special because, I'll do our usual wait. We won't be doing any quiz points this way. Oh, you're probably wondering what I'm going to do about that. Everybody will get 100% on all the quizzes for the rest of the semester. That's how we're going to handle that. Okay, so why is special relativity special? It's special because it only deals with frames in uniform motion relative to each other. Some students are confused by the phrase uniform motion. Here's what that means. Uniform motion means the 2 frames are moving at a constant relative velocity. I wish I could make this little inset window go away. This is going to mess up my slides. This will be a little rough. I'll get it figured out after a while. Okay, here's another one. The central idea of relativity is, which one of these? Some of these responses are kind of stupid. The surprising thing about relativity is that the correct answer is one of the stupid ones, that no matter what frame you're in, the speed of light is the same. This means that if you see light coming at you from a distant star, and you then hop in a rocket ship and take off toward that star at a very high velocity, say half the speed of light, so the light is coming at you at the speed of light, and you're going toward it at half the speed of light. This is what happens when you stick your hand out the window when you're driving down the freeway. It's pretty fierce outside the car, and if the wind is blowing toward the car, you put your hand out the window, the air is going by even faster. The speed of light past your rocket ship, if you're going at half the speed of light, ought to be about 1.5 times the speed of light. But what we measure when we do this experiment, and it's been done many times, is that the speed of the light as it goes past you, as you approach it at half the speed of light, is exactly the speed of light, 3 times 10 to the 8 meters per second. Well, where did this stuff come from? It came from wave physics, actually. So let's think about waves on the ocean for just a minute. If you fly over these waves in a helicopter at the same speed of the wave crest, so you're following them, in your frame, as you look down on those wave crests look like they're stationary. Those waves have 0 velocity in the moving frame of the helicopter. Now, you could go faster than the waves, and then they go backwards. You could go a little slower than them, and they go slow forward. But this isn't mysterious, because you look down in the water, you can tell that the water is moving. In the frame you're in, the water isn't stationary. The water's moving. And so there ought to be something funny going on here. Waves really ought to be observed to behave differently. when you're moving relative to them, when you have a moving frame of reference. This seems obvious. Well, in the late 1800s, Albert Michelson and somebody Morley went looking for this effect because the Earth is moving at a pretty high speed as it orbits around the sun. And they reasoned that if they looked at a distant star and checked the speed of light as it came past them when they were moving toward that star in the Earth's orbit, and then checked 6 months later what the speed of light was when it went past them, when they were moving away from the star, they ought to be able to measure a difference in the speed of light. And they measured this over and over and over again, and there was no effect. They got the same answer for the speed of light, whether they were at the part of the Earth's orbit where we were moving toward the star, or when we were in the part of the orbit where we were moving away from the star. Exact same answer. It bothered him. Bothered both of them, and they tried to work on this, and they checked it over and over again. They couldn't ever get any different result, and finally they just published it and said, well, this is what we got. It makes no sense, but here it is. So the result of this experiment was the light waves were always observed to move at 3 times 10 to the 8th meters per second, whether approaching the source of the waves or moving away from it. This is a big problem. Well, let's think about electromagnetic waves. We can't think about them very much because you haven't had it yet. But I showed you a picture when we first started talking about electromagnetic waves that showed that electromagnetic waves are combinations of electric and magnetic fields, and they actually make each other. When E is changing with time, when the electric field is changing with time, it makes the magnetic field B. And when B is changing with time, it makes E, and together, as they make each other through their changing in time, they make waves that travel at 3 times 10 to the 8 meters per second. When you look at Maxwell's equations, which is where this idea comes from, there isn't any medium really apparent in the equations. And so people were interested. They were trying to find the medium. That was the point of doing the Michelson-Morley experiment. Find the medium, find the speed of the medium that light is traveling in. And we have looked hard and hard for decades trying to find this medium, and we couldn't find it. About the time that this was all going on, a little before actually, young Albert Einstein, age 16 in high school, learning physics, and learned about electromagnetic waves making each other, he wondered what it would be like to catch a light wave. Suppose you were like the helicopter going over the ocean, and you caught up with the wave, and you looked down the window, and right below you there was a wave crest, and in your frame, your moving frame, it looked like that wave was standing still. Well, what would electromagnetic waves look like if you caught up with the wave? Suppose you went at the speed of light, so that the electric field is just frozen in that frame. It's not changing anymore because you've caught it. Well, the magnetic field would also be stationary, frozen, not changing in time. But that can't be because it's changing E that makes B and changing B that makes E. And if neither one changes, the wave can't exist. Well, this bothered him, and he thought about it for a long time. 10 years later, 1905, he proposed a crazy solution. He said, there is no medium for light. Everyone, no matter what moving frame they are in, sees light waves traveling at 3 times 10 to the 8 meters per second. Well, the only way to have electromagnetic waves exist and obey the laws you'll learn in Physics 220 in non-accelerating moving frames, if you believe that Maxwell's equations work in all moving frames, then you're stuck with this. The speed of light has to be the same in all moving reference frames. This is weird, but experiments show that it's true. So here's a quiz based on this idea. Suppose the spaceship is traveling directly at you at 1 times 10 to the 8 meters per second, and someone at the front of the ship sends a laser pulse out right at you, traveling at the speed of light in their frame. You see the laser pulse go by you at speed what? Which one of these? Give you a second to think about that. And the answer is 3 times 10 to the 8 meters per second. It doesn't matter what frame of reference you're in. If you're looking at a light wave, it will be moving at 3 times 10 to the 8 meters per second. Well, having the speed of light be the same no matter how you move is just nuts. But we checked it over and over again, and we seem to be stuck with it. Well, this is bad because this is crazy, and because this speed is crazy, it must lead to other craziness. And if you look at the units of speed, meters per second, what this turns out to mean is that distance and time turn out to be crazy as well when observed from different moving reference frames. And that's where the theory of relativity comes from. And here's partly what it says. It says, number one, events that are simultaneous in one frame are not simultaneous in a frame moving with respect to the first. That's crazy, and it's a direct consequence of the speed of light being constant for everybody. It also predicts that moving clocks run slow. It predicts that moving meter sticks are short. They're short along the direction of their travel. And of course, the fundamental assumption of relativity, which makes everything crazy happen, is that nothing can travel faster than the speed of light. Okay, so if you want to see a proof of the time dilation, or that moving clocks run slow, I invite you to go on YouTube, look up Mechanical Universe, find chapter 42, and watch this movie from frame 7 minutes 50 seconds in to 14 minutes 50 seconds in. I'm going to give you several viewing assignments from Mechanical Universe in the coming weeks, and this would be a good time for you to stop this recording and go look at that video clip. What you'll see in that video clip when you come back is that the moving clock, which is a light clock, it's simply the tick-tocks of the clock are made by a pulse of light bouncing up and down between two mirrors. If you now let that clock move, that tick-tock involves the light beam traveling a longer distance as you watch it go by, because it's not just going straight up and down, it's also going sideways and has further to travel as it goes between the mirrors. Well, normally we would say, yeah, but the speed of the light in that moving, the speed of the light I'm watching is the speed of light up and down, and then the frame velocity left to right. We'd use Pythagoras to find the speed, and it would be bigger than the speed of light. But no, that can't happen. That light pulse that's traveling that further distance as it goes tick-tock, tick-tock, the red bouncing, as you see that clock go by, that light is moving at 3 times 10 to the 8 meters per second, and it's going further than it goes when it's a stationary clock. Well, that means that moving clock has to be running slow. There's a formula for it in the theory of relativity, and it goes like this. The change in time, the tick-tock, the delta t tick-tock of the light clock in a stationary frame, watching it go by, is equal to gamma times delta t proper, where proper means the tick-tock time of the clock in its own frame, where it's not moving. And gamma is given by 1 over the square root of 1 minus v squared over c squared, where v is the velocity of the frame, speed of the frame, and c is the speed of light. Now, that 1 minus, that thing that's subtracted from 1, is incredibly small for all ordinary speeds. C is 3 times 10 to the 8 meters per second, and all of the v's that we normally encounter are so much smaller than this that after you square them and subtract them from 1, they're so far out in the digits of your calculator you can't even see them. And so this was not discovered experimentally. There was no way this was going to be discovered experimentally. It had to be discovered theoretically by deep thought, and that's what Albert Einstein did. In what follows, the word proper always means in its own frame, the frame of the moving clock or the frame of the own thing that we're talking about. And then the other delta t's and the lengths that we talk about are going to be as measured from a frame moving relative to the stationary object, in this case, the clock. Okay, well, length contraction. That's how you understand, or at least are hopefully convinced of, time dilation, or the slowing down of moving clocks. Why are moving meter sticks short? Okay, this is hard to do, so I'm going to do it by reference to an elementary particle called a muon, and I'm going to kind of tell you a story here, and the only way to make this story make sense is if length is contracted. So here's the story. A muon is an elementary particle that lasts for about 2 microseconds. That's their proper time from birth to death. The way muons are made here on the Earth is that cosmic rays come from outer space. These are heavy nuclei, often iron nuclei from faraway places in the galaxy, moving at very high speeds, close to the speed of light. They encounter the Earth and they hit the gas molecules in the upper atmosphere, usually nitrogen, and they hit one of these atoms and all heck breaks loose. When a muon hits the nucleus of one of these atoms, it breaks the nucleus apart into pieces, and one of those pieces that comes out of this horrendous collision is a particle called a muon. It's about like an electron, only it's heavier, about 200 times heavier than an electron, and it's unstable. It only lasts about 2 microseconds. Let's see if we should be able to observe one of these muons at the surface of the Earth. So the distance the muon can travel before it dies is equal to its speed. It comes out of the atom at about the speed of light, a little bit less. So you take 3 times 10 to the 8 meters per second times 2.2 times 10 to the minus 6 seconds, which is how long it lives. And the muon can only travel 660 meters. That's like 7 football fields. That's it. The atmosphere is way thicker than that. And so we shouldn't be able to observe these here on the ground. And yet, we do observe them. They're passing through your body right now. Not very many of them, fortunately, or you'd be dead. But there are some of them going through your body right now. They make it here. How? How do they make it here? Well, their life and death cycle is like an internal clock. And they're moving very fast, close to the speed of light. And so as we observe them tearing down through the upper atmosphere, that clock is running slow. It's got a gamma of about 730. And when you divide by that gamma, when you multiply that gamma to get the lifetime, multiply by gamma to get the lifetime as we observe it of the muon, it's gamma times 2.2 microseconds. And now, if they live that long, they can go 500,000 feet before dying. And so that explains why we experience them. Their clock, the muon life-death clock, is running slow, and they actually do reach the surface of the Earth, where we can measure their effects, and we know they're here. Well, now look, this is a problem, because from the point of view of the muon, it only lives 2.2 microseconds. And so if you're riding along with the muon and watching this experience, maybe it's a muon that's born 500,000 feet above the Earth and then dies on the surface of the Earth. What you see if you're on the muon is you see yourself be born at the upper atmosphere, and 2.2 microseconds later you die, but you've only gone 660 meters because the Earth is coming at you at close to the speed of light, and that's how much closer the Earth gets in 2.2 microseconds. This is an important thing to understand. Relativity makes the times and the positions of events be weird, but the observers in the two frames have to agree on the events themselves. So whether you're on the surface of the Earth or whether you're the muon, you know that you were born at the upper atmosphere and that you died after meeting the rock, dirt, and magma that the Earth is made of. Those two events happened. The only question is, when and where did they happen? So in both frames, the muon does hit the Earth. But if the muon can only go 660 meters in its own frame, how can it make it to the Earth? Well, the answer is that the thickness of the atmosphere in the muon's frame is a heck of a lot shorter than it is for us standing here on the surface of the Earth. That length has been contracted. The length is shorter by, in fact, the factor 730, that gamma factor. And so in the muon's frame of reference, here's what happens. It's born at the upper atmosphere. It only has to go 660 meters through this length contracted atmosphere, and then it hits the ground and interacts with another nucleus, and it dies. And this is called length contraction. This was actually discovered before Einstein. It's called often the Fitzgerald contraction. He's the first one who wrote about it. Lorentz discovered it too. And Lorentz discovered many of the details of relativity before Einstein. It's just that they didn't believe it meant that time and space was weird. They thought that it was some kind of optical illusion or something that made the formulas of physics be weird. What Einstein did was say, no, this is real. Space and time are completely screwed up. And that's why these funny formulas seem to describe what happens when you talk about things moving at close to the speed of light. Now, you won't have any helpful intuition about any of this. It won't make any sense. So how are you supposed to figure out anything? Well, here's how you do it. You write down the formulas, you learn how to use them, and they believe what they tell you. We'll learn next time that you can often make progress by inventing events like the muon death and birth, and inventing those events and looking at those events in different frames. It will help you figure out what's going on. To do that, well, you need to use something called the Lorentz transformation equations, and we'll do that next time. So here's how it works. The speed of light is the same in all frames moving uniformly with respect to each other. The factor gamma, which is always bigger than 1, is 1 over the square root of 1 minus v squared over c squared, where v is the relative velocity between the two frames we're talking about. The theory predicts that when you look at clocks go by you in a moving frame, that you see that clock running slow. It predicts that when you look at moving sticks going past you, you will measure them to be short. Let me emphasize here, this is not an optical illusion. If you perform a fancy experiment to measure the length of a moving stick, and you do it correctly and don't make any mistakes, you will find that that stick is short. This is not an optical illusion. It's not about what somebody sees. It's what you measure when you do careful experiments. And if you want to drive yourself crazy a little bit, think a little bit about how you would measure the length of a moving stick. So this isn't about being fooled or about what somebody believes. And let me warn you about those videos I'm assigning to you in the mechanical universe. They often use the word believe. He believes. Substitute for the word believes measures with careful experiments. It's not about what you believe or feel. It's what you actually measure when you do careful experiments. It's not an illusion. It's a law of the universe. Yeah, it's like that. Well, now some of you are thinking, well, okay, so maybe light clocks behave weird, but real clocks and biological systems like you and me don't have anything to do with the speed of light. Well, here's the deal. All mechanical processes, like springs and pendulums, and chemical processes, like the reactions in our cells that make life possible, all of these are governed by the laws of electromagnetism. And since the laws of electromagnetism behave in this weird relativistic way, all processes, mechanical, chemical, and biological, behave this way. There is no escape from relativity in the universe that we live in. All right, you have some questions that you can think about for next time. You'll have some homework to do. The homework is pretty simple. You just calculate gamma and use it in the right way. And it'll just get you used to these ideas, but there won't be very many very difficult problems. And I'm going to try to post this now in such a way that you can actually download it and view it. and we'll see if this is going to work. Hopefully it does, and then I'll see you next time.